Hello everyone, welcome to Lab 11. In this lab we're going to go over transformers, and it'll be sort of broken up into two parts. This first part will be on machine translation, and the second will be about the vision transformer. And so what we're going to go through here is basically how to implement a transformer from scratch. And as you can see on the right, I have the now famous figure from Vaswani et al.'s 2017 "Attention is All You Need" paper. And I'll keep that up throughout this portion of the lab just to keep referencing back to it as we talk about implementations. It'll, I think, be helpful to see where these things fit in. So just a quick outline of what we're going to cover in this section. Going to do just a very quick run through the data set and tokenization that we'll use. This will be pretty quick since this isn't actually particularly unique to attention and transformer architectures. It's more unique to language modeling and machine translation. And then we'll get into the actual model architecture of a transformer. So some of the basic building blocks, how to combine those building blocks into an encoder and a decoder, and then finally how to put those encoder and decoders into a full-on transformer encoder decoder model. In this case, again, applied to the task of machine translation. And just so you know, this notebook will be available online, so in case I scroll too fast, you can always access it. And we should say up front that the notebook borrows heavily from this source called the Annotated Transformer, which I highly recommend you check out, as well as, of course, the original paper. All right, so moving past all our libraries and imports. So in language modeling and machine translation, this idea of tokenization is pretty important. And basically, the idea here is that your models need numerical input. You can't just give it words. And so what we do with that is that we tokenize language into smaller pieces. So whether it be a full word, a portion of a word, punctuation, things like that, we can break it up and then we can encode it into numeric values. So at a high level, what's going on here is that we're just defining two tokenizers that we'll use for English language and for German, since those are the languages that we'll be translating from English to German. And so you can take a look through this, a couple of these custom functions and classes that we've made. But again, the focus here isn't so much on the inner workings of language modeling. But just so you know, essentially what we're doing is constructing vocabularies from the data sets we have for both English and German. Then we're going to use these to create a custom translation data set where we have our English data, our German data, the source tokenizer, the target, source vocab target. And all of this is relatively standard. You may even have implemented similar data classes such as these yourself. But again, you can reference the notebook if you'd like more detail. And again, just reading in our files. And to give you a quick example, when I talk about this idea of tokenization and then converting it to numerical data, this is what we're working with here. This is the actual data, but you can see that these numbers actually represent words in each of the two languages. So I don't know any German, but for instance, this sentence, a man in an orange hat staring at something, or maybe starring at something, would presumably be translated to this in German. And so that's the task that we're going to try and emulate. So now getting into the model architecture, we're going to go through a couple of the basic building blocks that a transformer is going to use. And so I'll be referring over to this piece here. And you might actually notice here that one thing we're sort of skipping over here, but is still important, is this idea of an input embedding, right? We're jumping right into positional encoding here. The idea of an input embedding, which we've, I believe, covered in class, is just the idea that rather than representing each word as a one-hot vector, which is sort of wasteful and doesn't capture any information about what it assumes an equal distance between all words, which may not be particularly reasonable. What we can do is just project into some model space, right? You'll see D underscore model used throughout this notebook, and it's just the model space that we're projecting into. And it's quite simple to do this. You can just use PyTorch. It has an nn.embedding, which you can use, and it's basically provides some learnable parameters that you can incorporate into your model. So running past that, we're going to get into positional encoding. And the need for positional encoding is because we're not using any sort of recurrence or convolution in our transformer architecture. So we're not actually capturing information about what words, in the case of language translation, what words are where in the sequences. So sort of explicitly, right, the multi-head attention that we're going to get to is permutation invariant, or sorry, equivariant. And so, right, it doesn't capture relative positions of words to each other. And as you can imagine, in language, that's quite important, right? And so we're going to use this mechanism called positional encoding to address this issue. And there are a few kind of desired characteristics that we mentioned in class that are listed here. One of them is sort of optional. You can have fixed embeddings, which I believe is what's used in the in Attention is All You Need paper. But an important one is that you have a unique embedding at each timestamp. And so the way that we're going to achieve this, and the way that they incorporate this in the paper, is that they use kind of alternating sine and cosine functions with different frequencies. And these frequencies are going to be based on the both the dimension of the model and the position in time. So explicitly, the formulas that they use in the paper are listed here. But as you can see, the two the things that are relevant here are the time position, the actual dimension, which is I, and then the overall dimension of the model. And just to give you a quick bit of intuition as to why this is helpful, the Attention is All You Need paper actually provides a really nice visualization of this, where they sort of show what these sort of wonky looking formulas actually do to data. So at a different point in time, you can see that these vectors will be pretty much unique as we add them, at least over a certain frequency. And so then what we're doing here is that we're just initializing a positional encoding matrix of zeros. And the size is going to be some maximum sequence length that we set ourselves, right? Maybe you set it to what's the maximum you saw in the data. Maybe you set it to something larger. That's up to you. And then the dimensionality of the model and of the input embeddings that we have. And then we perform these calculations and we fill in the positional embeddings, right? And then what we do in the forward pass is we simply add the positional embedding to the input we have, which is the, and sorry, I should say the positional encoding to the input embedding we have. And again, the reason this works, just to do a quick sort of toy demo here is that what we're doing, right, the formulas here is so some position, right, some position in time in the sequence divided by a number, right? And just to give a sense of what happens to the frequency of each of these sine waves when you, in this case, increase the denominator, right, as the frequency becomes larger, right? And then when you add in the cosines, you can get this. And then so at each time instant, right, you have what over a certain period of time is a unique vector for each dimension that you can add to the input dimension. Now, the issue here is that if we zoom out a bit, you can see that this repeats relatively quickly, right? So this is why they set some of these values to be what they are, so that it doesn't repeat so quickly, and that you can, over all the time instance in your data or in your max sequence length, you can have a unique positional encoding to add at each time instant, right? And that achieves this idea of a unique rotated embedding at each time instant. So I would encourage you, if you're interested more in this, I'd say read the original paper, and also the annotated transformer is a great resource for this. But again, the goal here and what we've accomplished is that we can now capture relative positional information for our application of machine translation, say the position of words to each other. Great. So next up is the concept of multi-head self-attention. And this is really the meat of the transformer. Again, the transformer, the kind of novelty of it was that this is one of the first architectures to not use any recurrence, not use any convolution, and primarily rely on attention. And so you'll see that these orange blocks of multi-head self-attention are prevalent throughout the model. Now, attention we've gone over in class, but it's essentially just a mechanism to allow you to account for context in a nice, parallelizable, efficient way. And so, for instance, for a given word in a sentence, you might want to heavily attend to a couple of other words in particular, but really not pay too much attention to others. So, for instance, let's say you're trying to encode some meaning from the sentence. Let's say, I left home, but I forgot my jacket there. So when you're on the word there, you would probably want to attend to the word home, right? Because that's what it's referring to. So that's just one kind of contrived example. And then you might also want to have multiple concepts to attend over. So for instance, the examples we give in this notebook are things like subject, verb, right? Adjective, verb, subject, object, right? And so you can essentially create multiple self-attention heads that can attend to different things, and again, achieve that across different concepts, achieve the goal of selectively attending to certain words based on the context of a sentence. And so within attention are going to be these three things that you may have heard of by now: the query, key, and value. And again, I think we've covered these in class, but at a high level, right, the query is sort of a request for information, an advertisement out saying, I'm interested in learning blank. The key says, yes, I have that information, or no, I don't. And then the value is the actual kind of information itself. And what the authors of Attention is All You Need use is a version of attention called a scaled dot product attention. And it's worth reading. They provide some justification of what and why they do this. But the actual calculation is just sort of this matrix multiplication, a scaling, masking, softmax, and then all of that together matrix multiplied. And you can sort of see why this achieves what we wanted to achieve. Again, at a pretty high level here, we're taking a query, we're taking a key, right? The query saying, I want this information. The key is saying, I have this information, and performing a matrix multiplication, right? So kind of a dot product. And dot products, to an extent, tell you how similar two vectors in a space are, right? So the more similar a query is to the key, the higher this value is going to be when it comes out of the softmax. And then once we have those attention weights, we can weight the values we have with another matrix multiplication, right? And then the idea of multi-head attention is just concatenating these various scaled dot product attentions together. Now, you might have noticed in the paper that there are 3 places where attention gets used, and they're actually used in slightly different ways. So first off is the attention in the encoder, right, which is sort of the vanilla version of attention, right, where it's just saying for the sequence that we're trying to translate, for a given word, how much do we want to attend to all the other words in the sequence? Next up is this, again, a self-attention, but we're calling it here cross attention because, well, if I can get back to this section, great. Cross attention because it's looking across to the encoder, right? So what's happening here is that this attention mechanism is actually querying to keys from the encoder to figure out what parts of the encoder output it actually wants to use, right? And then finally is masked self-attention in the decoder. This is quite similar to attention in the encoder, but notice the word masked here and think about why we might want to use that, right? What we're doing in, say, machine translation is translating a text from English to German. But the decoding here is going to be autoregressive. We're gonna decode one word at a time, and so it doesn't make sense to attend to words that you haven't spoken yet, right? It doesn't make sense to attend to things in the future, and so what the masking does is basically precludes you from cheating in this sense and looking to the future. So you can only attend to things that have already been decoded in this case. And just mechanically, a quick note here is that you can do this through almost kind of additive means where you have your mask that you add to your input or to your attention weights, and the mask just has negative infinity values in the places that you want to zero out. And the reason we do that is because we're going to pass it through a softmax, so those negative infinities just get converted to zeros and just have no effect. And just as a quick example, this is an image taken from the attention, or is rather the annotated transformer. And it's just an example of an attention map across English words and German words. So this would be an attention map from the cross attention that's looking back to the encoder from the decoder. So to the implementation, you can basically find most of these formulas either in the paper or in the annotated transformer. But essentially what we're doing is we have the dimensionality of the model. We have the number of heads that we want to capture different concepts. And then for each head, we have the head of that dimension, which is just the floor division of the total model dimension by the number of heads. From there, we define just learnable weights, or in this case, we're just defining linear layers, but those just have learnable weights. And what we do in the forward pass is we pass through our query key and value, which will actually just be the kind of positional encoding plus input embeddings that we're feeding in here for each of these. We pass that through the linear layer to get a query, a key, and a value. Perform a few operations here, and then perform the scaling that we had mentioned up above. So far we've done the matrix multiplication, just get to the scaling, right? And we're scaling by the root of the dimension of the individual head, right? And so at this point you have an attention mask, or a set of attention weights, effectively. This is a sequence length by sequence length vector that tells you for a given point in time how much to attend to other points in time in the sequence. You can then apply an attention mask. And again, we're using this negative infinity here, which we then pass through the softmax. And then finally, so these are the attention weights after masking. And then we use those along with the values, and then perform some operations here just to effectively concatenate all of the different attention heads together. And that is our multi-head attention. So again, that's the meat of the transformer. From here, the pieces get quite a bit simpler. Next up, you'll see in yellow, there are these add norm blocks, which are pretty much what they sound like. If you remember back to things like our implementation of a ResNet, right? There's this idea that adding residual connections will make training easier. In this case, right, it makes gradients a bit more stable. So that's effectively what we're doing here. It's a very simple class, just taking a norm of a residual connection and passing that forward. Next up in blue, you'll see this feed forward network, which is effectively just a simple MLP, like a fully connected layer that in this case just has, you pass through a linear layer, some activation, in this case just a ReLU. You can optionally add some dropout, and then just through another linear layer. And again, you'll just pass that into an add a norm. And then that is effectively, once you combine those together, that would be, for instance, your encoder output. And so, yeah, I guess we jumped ahead a little bit here, but now that we basically have all of the pieces we need to construct an encoder and a decoder, right? We have our attention, we have our add a norm, we have our feed forward. We can construct each of these larger pieces of a transformer. So as I just mentioned, the encoder takes the input embedding plus the positional encoding, and then passes it through an attention layer, add a norm, feed forward, add a norm, right? And so we initialize each of the pieces that we will need here, and then simply pass it through each of those pieces. And as I mentioned, what we're doing here is just passing the input X as the kind of query value, the key value, key and value values, and then optionally a mask as well. But this, you'll see, just matches pretty much exactly with what we see in the paper here. Now, the decoder is a little bit more interesting, in part because of this, both the cross attention that we mentioned as well as the masked self attention. But it's still not too complicated. We initialize each of the building blocks we defined above. And then, as you'll see, we take the embedding from the output that's being generated, as well as the positional encoding, and then pass that through our first masked self-attention layer. And you'll notice here we're using the target mask to mask that. Then a norm. And then, as I mentioned earlier, this idea of cross-attention, you'll notice here that what we're passing through is the output we have from our add a norm as the query. So this will kind of advertise saying, I need X information, right? And then the keys and values actually come from the encoder's output, right? So we're querying the encoder for information here and then using that. And then we can apply a source mask to that as well. And then from there, it's quite simple. Again, it's just some norms and a feed forward. And then from there, you can pass through a final linear and softmax layer. And so that effectively, those are the pieces that we need. And so just putting the entire thing together into a transformer architecture, we are going to use, again, our embedding layers just straight from PyTorch. We are going to initialize positional encoders. And then we have encoder layers and decoder layers, right, based on everything we've just discussed. And then finally, a fully connected layer with a linear layer just for output. And that is effectively it. The code from here is pretty simple because we've already defined these pieces. So now we can actually use this transformer architecture that we've created. And again, the application here is machine translation. So you can check the notebook, maybe toy around with some of these hyperparameters. We're going to use a bit of a special scheduler that you may not have used before, which was taken largely from this annotated transformer paper. But again, you could experiment with other schedulers. And then we define our model using our source vocab size and the different hyperparameters that we set. You can check the notebook for a couple of these target and source masks just to get a sense of how we're doing that. And then finally is just a function to calculate a blue score, which is a score that's typically used to evaluate translation tasks. And basically, I believe the higher the better for this. So from here, feel free to pick through the notebook, take a look through the model summary. You can see it's a pretty small model, but the punchline here is that with some pretty classic training, validation, and inference functions that I'll let you take a look through, you can train this model and you can see the blue score and validation loss become more favorable over time. There's maybe a bit of overfitting that's happening here, but we can get a model that learns here. And then when we pass a few examples through our trained model, we can get relatively good results, where if we have this source sentence in English, the machine translated sentence into German is quite close to the ground truth that we had just in this one instance. And so with that, I'll wrap it up. But yeah, please take a look through the notebook, the original paper, which is very nicely written and just it's actually quite simple to read for such a powerful step forward in the technology. So it's definitely worth a read. And then for a much more in-depth thing, I can't recommend the annotated transformer enough because it's a great resource. So yeah, please reach out if you have any questions. But this has been part 1 of the Lab 11 transformers with the focus on machine translation.